Hello everyone, we're going to be going over section 9.3 today, which is on the complex plane and de Boer's theorem. So we have 5 objectives today. 1, we want to plot points in the complex plane. 2, convert a complex number between rectangular form and polar form or exponential form. 3, find products and quotients of complex numbers. 4, use de Boer's theorem. And 5, find complex roots. So start with objective 1, we want to plot points in the complex plane. So a complex number z is going to be equal to x plus yi, and this can be interpreted geometrically as the point xy in the xy plane. Each point in the plane corresponds to a complex number and vice versa, and the collection of such points is referred to as the complex plane. So in essence, we are adding on to our original xy plane to now create the complex plane. The x-axis is referred to as the real axis since any points that lies on the real axis is of the form z is equal to x plus 0i, which is equal to x, which is a real number. So our x-axis is going to stay the same, essentially. But the y-axis is referred to as the imaginary axis since any point that lies on the imaginary axis is of the form z is equal to 0 plus yi is equal to yi, a pure imaginary number, or y is some number and I is the value that makes that number imaginary. So if we look at our image here, this is what any point on a complex plane would end up looking like. We see our x-axis here. This is still the real axis. It's pretty much the exact same as our xy plane, but now our y-axis is the imaginary axis. And then we have any point z, which is then equal to x, so whatever point you have on your real axis, plus yi. So y is going to be some value that you would normally see on your y-axis multiplied by the imaginary number. So, all right, definition, we have a magnitude or modulus. So suppose z is equal to x plus yi is a complex number. The magnitude or modulus of z, denoted as z within absolute value bars, is the distance from the origin to the value of x comma y. That is that the magnitude or modulus of z is equal to the square root of x squared plus y squared. Then we get the definition for magnitude or modulus is consistent with the definition of absolute value, since the absolute value of z is equal to the square root of x squared plus 0 squared if y was equal to 0 is equal to x squared, which is equals to the square root of x squared, which is equal to the absolute value of x. So we have the magnitude or modulus of z is equal to essentially the absolute value of x. Because of this, the magnitude of z is sometimes referred to as the absolute value of z. So sometimes we can refer to it as both absolute value and magnitude. Then recall that if z is equal to x plus yi, then its conjugate is denoted as what we call z bar. It's z with a bar above it, therefore we call it z bar. As z bar and z bar is equal to x minus yi. So remember that conjugate is just going to be the same values with the opposite sign. Then since z times z bar is then equal to x squared plus y squared, this is a non-negative real number, we get that the magnitude of z would then be equal to the square root of z times z bar. All right, on our first example, we want to plot the point corresponding to z is equal to the square root of 3 minus I in the complex plane. So we have our complex plane here. We see our real axis is our x-axis here, and then we have our imaginary axis. So if we want to begin to work through this problem, we see that z is equal to the square root of 3 minus I. So remember, this is our, way too big there. The square root of 3 is our x value, and negative I is our y value. So this means since z is equal to the square root of 3 minus I, is going to correspond to the rectangular coordinates square root of 3, comma, negative 1. And we see here this is because our square root 3 is always going to correspond to that x value. Then when we have some value that's multiplied by I, that value is going to be your y value. So in our case, it is technically going to be a plus negative 1 times I. So negative 1 would then be our y value, which remember is also our imaginary value. Or it will be plotted on our imaginary axis. So since we want to plot this point, we would need to end up finding the square root of 3 on the x-axis and negative 1 on the imaginary axis. So the square root of 3 is a value that's in between 1 and 2. So we want to find this point. It's about right here, square root of 3. And then we plot our next point, which corresponds to our imaginary axis, negative 1. So our point z is about right here. So this is z is equal to the square root of 3 minus I, which is also the point square root 3 comma negative 1. So there we go. Whenever we have an equation or whenever we have a complex equation, we can very easily deduce what's going to be the values that we go with according to our x and y axis there, which is now our real axis and our imaginary axis. So it's really just picking out which values correspond to what values in rectangular coordinates. All right, so objective 2, we want to convert a complex number between rectangular form and polar form or exponential form. So when a complex number is written in the standard form, z is equal to x plus yi, it is in rectangular or Cartesian form since x and y are the rectangular coordinates of the corresponding point on the complex plane. So once again, whenever we see x and y is being used, we know that this is going to be in rectangular coordinates because otherwise you would use exponential form or you would use your polar form, which would then be r and theta. So remember that if we let our x equal r cosine theta and y is equal to r sine theta in our polar coordinates, so we end up getting the polar form of a complex number. So that means that if r is greater than or equal to 0 and theta is between 0 and 2 pi, not including 2 pi, the complex number z is equal to x plus yi can be written in the polar form as z is equal to x plus yi, which we replace x and y with their polar forms, so we get that is equal to r cosine of theta plus r times sine of theta times I, which then we can simplify further to say r times cosine of theta plus I times sine of theta. So now we have the conversion for our complex number here in polar form. So if z is equal to r times cosine of theta plus I times sine of theta is in polar form of a complex number, then the angle theta, which is between 0 and 2 pi, not including 2 pi, there we go, is called the argument of z. So that's what we call the argument of z. Then, since r is greater than or equal to 0, we're going to get that the magnitude of z is equal to r times cosine of theta plus I times sine of theta, which we can simplify to just be that the magnitude of z is going to be equal to r. We can also use Euler's formula. So for any real number theta, e to the power of I times theta is going to be equal to cosine of theta plus I times sine of theta, which then we can go ahead and replace our cosine of theta plus I times sine of theta with e to the power of I times theta. So we can now say that r times cosine theta plus I times sine of theta is equal to r times e to the power of I times theta. When a complex number is written in the form of z is equal to r times e to the power of I times theta, it is said to be written in exponential form, where theta in this case is always going to be in radians. So whenever you have an exponent e, you're going to be in exponential form. Whenever you have anything in terms of r and theta, without any exponential form, that's going to be polar form. And then whenever you have x and y, that's going to be in your rectangular coordinates. So for example 2, we have z is equal to the square root of 3 minus I again. But now we want to write this in polar form and exponential form. So let's start with polar form. So if we begin with polar form, we get that x is equal to the square root of 3 and y is equal to -1. So when we replace our values, we're going to get that r is equal to the square root of x squared plus y squared, which is going to come out to the square root of 3 squared plus -1 squared, which is the square root of 3 plus 1, which is just the square root of 4, which is equal to 2. So we have that r is equal to 2. Then cosine of theta we know is equal to x over the value of r. We know that x is the square root of 3 and r is 2, so we have that cosine of theta is equal to the square root of 3 over 2. And sine of theta is equal to y over r, which y is -1 over r, which is 2. So sine of theta is -1/2. And we see here that theta is greater than or equal to 0 and less than 2 pi. So now we can determine that the angle that satisfies both equations is going to be theta is equal to, and at this point you can look at the unit circle, you would be able to find this value fairly easily. Theta is equal to 11 pi over 6. And we also do have that r is equal to 2. So we can find the polar form. So remember our polar form was z is equal to r times cosine of theta plus I times sine of theta. So we write out that this equation is equal to 2 times cosine of, and now we replace theta with 11 pi over 6, plus I times sine of 11 pi over 6. And this will be our polar form. As we see, we have rewritten our equation so that now we have r and theta written in their actual values. So this would be in our polar form. Now, then we'll write our answer in exponential form. We already have our polar form, so it's going to be that much easier to write out our exponential form, since we state that our exponential form, we are essentially just replacing cosine of theta plus I times sine of theta with e to the power of I times theta. So our exponential form is going to be 2 times e to the power of I times 11 pi over 6. So in problems like these, it's very helpful to go ahead and solve for your polar form first, because then you can really easily switch that over to your exponential form.